In this video, we're going to look at regression and correlation and see kind of what's happening with it. So, regression is where we have to have some variables. The variables are response and explanatory. You could also have things called covariates, which are additional variables that could explain the response in addition to the explanatory. Regression finds the relationship between a response variable and one or more explanatory variables. Linear regression is going to find just the linear relationship between a response variable and one or more explanatory variables, and that's, in this course, we're only dealing with linear. A visualization is a scatter plot of the data with explanatory variable and response variable. The regression equation is where you're going to find the regression equation, which is also sometimes called the least squares line or the best fitting line. A regression equation is where you're going to have the response variable is equal to some intercept, that's where it crosses the vertical axis, plus the slope times your explanatory variable. If you have covariates, then you'd also have the covariate for the slope times the covariate for every single combination of covariate. Then you can also graph the regression line on the scatter plot to see how well it fits the data. Prediction is where you insert the value or values of the explanatory variable or variables into the regression equation to predict the value of the response variable. The coefficient determination, this is the percentage of the variability in the response variable explained by the explanatory variable or variables, or you can just say the model. Correlation coefficient is how strong the relationship is between the response variable and one explanatory variable. You cannot do correlation on more than one explanatory variable. This is why a lot of statisticians don't use correlation coefficient anymore. So I have an example. I believe that foot length and height are related. So this data was collected from my students in my class. The data set is called foot height. I need to get this data set going, so I'm going to go back up here to my R chunk, run this R chunk. I do need the package mosaic. Here's my data set. I had to recode some of these so that my male and female were both the same size letters. Okay, now back to my example. So I can glimpse what this looks like. I can see I have sex, I have length, and I have height. So my variables that I'm working with, since I believe your foot length is predicted to your height, I believe that the response variable is a person's height. I think you can predict somebody's height from the length of their foot. That means the predictor variable or the explanatory variable is the foot length. I'd like to kind of do a visualization of it, see what it looks like. So we're going to do a scatter plot. We are doing a plot. We are in the mosaic package, so GF for graph function. And then this is a scatter plot, which is just a bunch of points all over the graph. So that means it's GF point. Then we always start with our response variable, tilde our explanatory variable, which in this case, it's foot length, but it's just the variable is called length. If you want to, you can look at your data set, make sure that's what it's called. And then my data is equal to height, foot. I'd like to have a title. Title might be something like foot length, height versus foot length. And then I might go ahead and do an xlab, and this would be the length of a foot. And this was in inches. And then I might do a ylab, and that would be the height and also in inches. And I can graph it up. And looking at this, I can kind of see there is a general trend. People with longer feet are taller. People with shorter feet are shorter. There does seem to be kind of a linear trend to it. So that makes me want to find a linear relationship. So we'll do a regression equation, we'll find a linear relationship. I want to find a linear model. So LM for linear model. And I'm going to put in my response variable, which is height. is related to, that's what that tilde means, and then length is the foot length, and that's my explanatory variable, and my data set is, again, height, foot. I can run this, and what this does is it tells me that I was finding a linear model. My formula is height related to length, and my data set, and then it tells me my coefficients. My intercept is my vertical intercept, where it crosses the vertical axis. My coefficient for length is the slope. So I can now write this equation. You can write y and x's, but I prefer to just use my names. So I have height is equal to 38.01, let's say, plus 2.98 times the length. If I want to, I can draw this on the graph to see what it looks like. So the way I have this happen, I can put it up here if I wanted to, or I can just go ahead and copy this, create a new R chunk, paste it in there, and then, so remember the and then means you need a piping symbol. So the vertical line and the greater than symbol, hit enter, and then you're going to do a GF. I want to graph my line, so GFLM for my linear model. Hit tab. I don't need to type anything else in here because what piping really does is it also uses what was in the previous one in the next one. It pipes it into it. So if I just hit go, it'll draw it on there, and you can kind of see some of the points fall on the line, some are above the line, some are below the line. That makes it the best fitting line because you're trying to minimize that distance, those distances. I'd like to now use this line to predict. My foot length is 9.75 inches. I would like to know how tall I am. So let's go take our equation. And instead of length, I'm going to type in my 9.75. I can either pull out a calculator at this point, or I can use R to do this. So I'm going to put an R chunk in. I don't want to put the height equals because R doesn't know how to deal with it. I just need the numbers. So I'll just copy the numbers, paste them in here, and then R will now do this calculation for me. And it says it's 67.065 inches. So that's 5'7". I'm actually 5'6". And so this is slightly off, not that far off, but slightly off of what my real height is. My brother Michael's foot length was 13.5 inches. I'd like to know how tall he was. So again, I'm going to do the same thing. I'm going to take my equation. Instead of putting in then my height, my length of my foot, I'm going to put in the length of his foot. I'm then going to calculate that for my brother. Put in the 13.5. And that comes out with 78 inches. So that means my brother, so I was 5'67" inches, which is again 5'7" inches. My brother Michael was said to be was 78 inches, and that is 6 feet 6 inches. So I'm actually 5'6", so this is close. It's not great, it's not perfect, but it's close to my height. My brother Michael was 6'4", so this is pretty far away from actual his height. My value of 9.75, that actually was inside my data. You can see that that's actually part of my range of data values. They went from 8 all the way up to 12 inches. So my height is somewhere in here. My length of my foot is somewhere in here. This line will predict it pretty good. It's what we call interpolation. This is where you're predicting a response variable from an explanatory variable that's inside the original data. My brother Michael, on the other hand, if you look at his, 13.5 is outside the original range of the data. No, it's not on my graph. There's no dots over there. That's called extrapolation. And this is when you predict a response variable from an explanatory variable outside the original data. Extrapolation is inherently worse. At predicting. Next thing I want to do is find the coefficient of determination. One thing I noticed is if I did 10 inches, let's say, because there's a lot of people with 10 inches, there are a lot of people with 10 inches for foot length, but their heights were all over the place. So there is variability in their foot length based on that. So we'd like to know how much variability is there in somebody's foot length, somebody's height based on their foot length. And notice as we get farther out, there's less variability, probably because there's less numbers there. But there's some places there's more variability, some there's less. So let's find out how much. The way we do this is the first thing I have to do is I actually need to save my linear model I created with a name. So I'm actually going to give it a name. I could have done that up there, but I didn't. And I'm going to call it something like LM out, LM underscore out, just trying to give it a name. And I'm going to do my linear model creation. Notice it didn't seem like it did anything, but it did create something over here in my global environment. And then I can run this, and then I can actually say, okay, now what I want to do is I want it to find me the R squared. Because that's actually what the coefficient determination is it actually is the R squared value. So if you type in R squared, and then you say you want to do it for LM out, that model we just came up with, you can run this, and it comes up with 48.2, let's say. So that means that 48.2% of the variability in height is explained. And you can say by the model or you can say by the foot length. It's up to you which way you want to do it. Which means that's not bad. 48% of it is explained by that. The fact that there is difference in people's heights is explained by the length of their foot. There are probably other things that also explain it, but that's kind of what it comes up with. Since it's 48.2, that means there are some other variables that could be affecting it, and that's where covariates come into play. Let's do the correlation coefficient. The way you do that is you just type in core for correlation, and then you type in your height, your length, and your data is equal to foot length, height foot length. Run that. Oops. I need to use my tilde. I apologize. So height tilde length. Now I can run that one. So again, it's your response variable tilde your explanatory variable. And this is relatively okay. It's a moderate, what we'd say. Moderate correlation. Just means how strong it is. So it's a moderate correlation. There's this, and it's positive. So I probably should say moderate positive. It's not great, but it's not bad. Now let's think, could there be another variable? 48.2 is not great. Are there other variables that could also explain it? That's what the covariate comes into play. So we're going to do the same thing. We're going to increase in our chunk. We're going to go ahead and create a graph again. So we'll do our nice little graph here. Just copy this again. But this time I'm going to put a covariate in it. I'm actually going to add a covariate into this graph. And the way you do that is you just say color equals tilde the other variable. The only other variable I have to work with is sex. If you have more variables, you would just add those in. But that's all I have to work with is that sex variable. So that's the one I'm going to work with. And color will then separate it based on that. So this basically is faceting. And you can now see that females all down here, males are a little bit higher up. And so it gives you an idea that there does seem to be a covariate, there does seem to be something going on there. So that says to me we can find a relationship here. If you want to see the graph, we can do the graph first. Let's do that. So we're going to do a and then. GF underscore LM. And again, what that will do is that we'll just put on the regression lines. And so you can see there are two different lines because there's two different slopes. And so we can get that kind of an idea. And so we can go find those regression. Again, and I'm going to go ahead and save this one. We're going to call it LM out 1. So we write over the one we already have. And then we're going to do LM. And we're going to have our length of my height, my response variable, tilde, my explanatory variable, which is length, but it also is sex. So we're going to add to that. So you just do plus sex. So it's just length plus sex. And then my data set is, again, height foot. When I run this, nothing will look like it happens. So I'm going to actually tell it I want to actually have it display the LM out, LM1 out. So it also displays it. So now I can see I've got more involved in this. So what I can now say is my regression equation is that the height is equal to the intercept of 48.3 plus my length of 1.7376, times my length, plus 3.45 times my sex. And it does say sex M. That will mean that males would be a 1 and female would be a 0. So if I wanted to find my height now, with my length of my foot is 10 inches, then I would use the same formula. And for my sex, I'd put in 0 because I am female. My length, and granted, this is still doing female, male as binary. I realize that they're not always 9.75. And then ask R to calculate that for me, and I'll come up with my answer. And it tells me that I should be 65.46 inches tall, which is closer to what I really am, because I am 5'6". I'm a little bit less than 5'6", so that's pretty dang close. I can do the same thing with Michael's. I could find his height. My brother Michael was male, so I'd put a 1 in for male, and then I'd put in my 13.5, and then I can go calculate that and see what I come up with. And it tells me that he should be 75.51 inches. Still taller than he was, really, because he was 6'4", but not too far off, actually. Actually, it's almost right on, now that I think about it, because 72 inches plus 4 would be 76. So it almost is perfectly what his height was. So this means it does a pretty good job, and we can actually find out how good of a job it does by finding the R squared. And that has done my linear model out to 1. And run that. And that is 59, almost 60. So 60% of the variability in height is explained by this model. So that's pretty good. I can't find the correlation, but I can find the coefficient determination.